Bismillah ar-Rahman ar-Rahim. Are you hearing my voice? Yes? Okay, we introduced in last week the phasor concepts and also the active power, reactive power, and power factor in single phase lines, and continue with the complex power. Let's see. Okay. If you consider S complex power equal phasor of V and I conjugate. V is the phasor of voltage and I is the phasor of current. We can write V with angle delta and I angle beta in general form, and if you apply the conjugate in B, we have the VI delta minus B. Please see this here, V is the magnitude of voltage and I is the magnitude of current, and here is the angle of voltage minus angle of current. We can write with the Euler identity VI delta minus beta. We can write VI cosinus delta minus beta plus J VI sinus delta minus beta. The complex power has a real part and imaginary part. Here is delta is the angle of voltage, beta is angle of current, and we can write in general for S equal VI cosinus delta minus beta plus J VI sinus delta minus beta. Okay. We can represent complex power S equal P plus JQ. Please see. Here, VI cosinus delta minus beta is the active power, and VI sinus delta minus beta is the reactive power. This is the active part, and this is a reactive part. And you can write S equal P plus JQ. Okay? For example, please see, we want to calculate real and reactive power delivered or absorbed. For example, a single phase voltage source with V equal 100 with angle 130 volts delivers a current I equal 10 with 10 angle, which leaves the positive terminal of the source. Calculate the source real and reactive power and state whether the source deliver or absorbed of each of these. Please see. I active the. This means we have a voltage source. This is the load. Okay. This is the current. And here is voltage. This is positive terminal and the negative terminal. The single phase voltage source here, V equal 100 with angle 130 and I 10 with angle 10. Okay, we can write now. Please refresh your screen. Other students have my voice? Okay, for this example, you can write the complex power with this formula. S equal VI conjugate. This will be 100 with angle 130. This is the voltage, phasor of voltage, and the 10 with angle 10 conjugate. Okay, in this here we can write 100 multiple on 10, 1000 with angle 130 minus 10, because we apply conjugate here. S will be 1000 with angle 120, and you can write by Euler formula 1000 multiple on cosinus 120 will be 1000 multiple on minus 0.5 will be minus 50 plus j. 1000 sinus 120 will be j 866. Real part of the S is minus 50 watts, and imaginary part will be 8666 bar. Okay. In this here is the reactive power. This is active power. Active power is minus 500. This represent the source absorb 500 watt and deliver 866 watt. Because this sign minus, this means absorb, and this is positive, means deliver. Okay, this is an example for apparent power or complex power. For resistor and inductive and capacitor, we can write for complex power. For example, SR, the complex power for resistor will be VIR conjugate, V with angle delta, and IR VR angle minus delta will be V2 divided R. Please see the imaginary part is 0. This means resistor only have active power and the reactive power is 0. And for inductor, we can write VIL conjugate, V with angle delta, V divided minus JXL with angle minus delta will be plus JV2XL. This means the real part of this inductor is 0. Okay, this means inductor only has imaginary part or reactive power. And for capacitor, we can write VIC conjugate, V with angle delta, V divided minus JXC with angle minus delta, and we can reach to minus JV2XC. This is the imaginary part, but please consider the minus in capacitor. Please see this sign, minus, but in inductor is plus. This means the complex power in inductor and complex power in capacitors are in different sign. One plus and second is minus. And the resistor has not any reactive part and only have active parts. Okay. You can write for S S is the magnitude of the complex power. S is equal P2 plus Q2 under radical, okay, and the delta minus beta equal tangent minus 1 QP, or Q equal P tangent delta minus beta, and power factor or cosinus delta minus beta equal P divided S, or P radical P2 plus Q2. Okay, this is the main formula for representation of the dependency of P, Q, and S. Okay. Let's see the example 2.3. It is application of this formula in numerical example. A single phase source delivers 100 kilowatt to load, operating at power factor of 0.8 lagging. This means, let's see, we have a in this year, let's see, the source deliver 100 kilowatt to this load in power factor equal 0.8 lag. Let's see. Okay. Calculate the reactive power to be delivered by a capacitor connected in parallel with the load in order to raise the source power factor to 0.95 lagging. Also, draw the power angle for source and load. Assume that the source voltage is constant and neglect the line impedance between the source and load. It is a very important problem, and I want to calculate this in the whiteboard. Please a moment. I find whiteboard for you. Whiteboard. Whiteboard. Okay. Again, I explain the example. Please see here. We have a voltage source. Here is a load. Okay. We deliver from this source to the load 100 kilowatts. And the cosinus phi or power factor of a load equals 0.8 lag. Okay. The problem wants us for connecting a capacitor in parallel of the load, and we want raise the cosinus phi to new cosinus phi equal 0.95 lag. Okay. Come back to our slides. Let's see again. A single phase source delivers 100 kilowatt to a load operating at a power factor of 0.8 lagging. For example, in induction motors and others. Calculate the reactive power to be delivered by a capacitor connected in parallel with the load in order to raise the source power factor to 0.95 lagging. Okay? The problem wants calculate the reactive power to be delivered by a capacitor connected in parallel. Okay? Assume. Also draw the power triangle for the source and the load. Assume that the source voltage is constant and neglect the line impedance between the source and load. It is not any impedances between source and load. Okay, please see. For solution, the circuit and power triangle are shown in figure 26. I will show the real power equal P equal PS equal PR delivered by the source and absorbed by the load is not changed when the capacitor is connected in parallel with the load, since the capacitor delivers only reactive power QC. For the load power factor angle, reactive power absorbed and apparent power are theta or phi equal lambda minus beta L cosinus minus 0.8 equal 36.57 degree, and QL by this formula, Q equal P tangent phi L or theta L equal 100 tangent 36.85 and 75 kilowatt, and SL will be P divided to this. It is here. Please see here. The S, please see S equal P divided to PF. P divided to cosinus phi, and you can reach to 125 kilovolt ampere. Please see this triangle. This here. This here is the power by source, power by load. It is not changed when apply capacitor. Okay, no problem. And this is a S before applying the capacitor, connecting the capacitor. After connecting the capacitor, S decrease to this amount, and angle between current and the voltage or phi from this amount decrease only to this, from 36.87 decrease to 18.19. Okay, the summation of Q is 75, and we can reach to 32.87 kilowatt. This is the amount of capacitor reactive power connected to the load. It is clear? Need to explain again? Right, alors, now you need You need for repeating the problem again? Okay, Ahmad, I explain in the whiteboard again. Please see. Please see here again. We have a single phase source here connected to general RLC or load. Before connecting capacitor, the load absorbs 100 kilowatt and cosinus phi equal power factor equals 0.8 lag. Okay, no problem this here? Okay. I want to draw the triangle, power triangle before connecting capacitor. Please see. For triangle, we need active power. Active power equal 100 kilowatt. Okay, 0. And the reactive power equal, this here, this here, Q equal P tangent delta minus beta. We need to calculate delta minus beta for calculate Q. Please see here. Okay, Q is P is a multiple on tangent theta or phi. Phi or theta is delta minus beta. Okay, no problem here. We need to calculate difference of angle between the voltage and also the current. Please see here. For finding delta minus beta, we have cosinus phi or cosinus delta minus beta here, excuse me, here. Delta minus beta equal 0.8 lag. Okay. For finding phi or delta minus beta, we can write delta minus beta or phi or theta equal cosinus minus 1 0.8. This will be 36.70. Okay. For Q, we can write P tangent phi. We can write 100 kilowatt multiple on tangent 36.78. Okay, if you apply this formula, you can reach to Q. In this calculation, Q will be 75. Okay, please see. V4, I write here, V4. V4 connecting capacitor, before connecting capacitor, we have P equal 100 kilowatts, okay, and Q will be, let's see, Q will be 75 kilowatt. In this condition, cosinus phi or power factor equal 0.8 lag. Okay, let's see. For power triangle, you draw the P in the horizon direction. Here is P. P equal 100. And in this here, for lag, this direction you draw 75. Okay. If you connecting this here to this here, this will be S. S, this is the 90 degree. S will be 75 plus 100. Okay, 75, 2 plus 100, 2, this is a 2. This will be magnitude of S, and this angle will be 36.78. You see? This is the next slide. Okay, this is a triangle before connecting capacitor. Okay, the problem asks for calculating the capacitor when we want to reach from 36.78 to this degree. This degree is cosinus minus 1, 0.95. We want from 0.8 to reach to 0.95. Okay. In this here, we calculate cosinus minus 0.95. In this condition, let's see here. Okay. Let's see. The next is okay. For cosinus minus 0.95, you reach to 18.19. In this condition, cosinus after connecting capacitor, Q will be P 100 tangent 18.90 will be 32.87 kilowatt. Okay, this is a kilowatt of a load and capacitor B after capacitor connection, and 75 is the reactive power B for capacitor connection. Okay, for calculating the reactive power by capacitor, you need only 75 minus 32.87. This will be QC. Okay. And if you, are you kidding here? If you represent the triangle before and after capacitor connection, please see this triangle is before capacitor connection. This triangle is after capacitor connection. Okay, P is not changed before and after capacitor connection, but reactive power from 75 decrease to 32.87. This will be QC. For QC, we only need to calculate 75 kilowatt minus 32.87. We can reach to this here. Okay. This is a complete example for drawing the triangle, power triangle. Okay. In reference book, you have a software and you can calculate by software. Software is special for this source. Okay. If you agree, we have a break for 10 minutes and come back after 10 minutes to lecture. Thank you for your consideration. Please go for drinking and eating some lunch and come back to the lecture. Okay, Ali Sadr, after come back to lecture, I will describe about the capacitor allocation in systems, okay? Thank you so much. Please go for drinking tea or coffee for 10 minutes. Thank you. For example, in factories, okay, it is correct. Then we deliver power from a distribution network or power system to this factory. We record here kilowatt hour and kilowatt hour. Let's see, the owner of this factory pay for kilowatt and for kilowatt. Okay. For active power pay dinar, real, dollar, and others, and also the owner of this factory pay for Q also. Okay. For this reason, price or cost dependent to P and Q, the owners of this factory try to connecting capacitor for decreasing of kilowatt from distribution network, and this owner try to decrease the price for electricity. The price of electricity, including price of kilowatt hour and kilowatt hour. For this reason, the owner of this factory try to connecting capacitor for decreasing kilowatt hour from distribution network. Okay, this is called, I write here, reactive power compensation. For power factor improvement. Okay. Connecting the capacitor in factory over large load for increasing the power factor is reactive power compensation for power factor improvement. Okay. For utilities, for example, distribution companies, if you consider a distribution network, the operators of distribution network connecting in some places capacitor for decreasing of loss in the network. Okay, this is called reactive power compensation by utilities for loss reduction or voltage improvement. Is this correct? Please see, reactive power compensation for power factor improvement is used for owners of the factories or large consumer and others, but reactive power compensation by utilities for loss reduction or voltage improvement are done using distribution companies and others. Okay, please see. For this reason, we need to allocate optimum point for connecting capacitor. This is called the capacitor placement for loss reduction. Okay, Ali Sadr, it is correct? Okay, I want to come back to our lecture and continue. Okay. Okay, I want to introduce for you the concept of the network equations. Please see, I want to use the whiteboard for network equations. Please see. Please see, it is the base for load flow calculation. Please pay attention. Please see here. For example, we consider a network with 3 bus or 3 nodes. Okay. This is node 1, this is node 2, this is node 3. This is a impedance between 1, 2. This is impedance for 2, 3, and here a reactance between 1, 2. In generally, you can consider if we have a resistance here, we can write Z, impedance between 1, 2, impedance between 1, 2, 1, here 3, 1, 3, and here is impedance between 2, 3. No problem? Okay, please see. Here, maybe we have generation or maybe have load. We have injected current from generation to the bus. I write here I, J, G, 1. This means injected current by generator in bus 1. Here is the absorbing current from bus. This right, I load in bus 1. Please see here. I summarize this by I1 equal generated current by generator minus G1 minus current by the load. Okay, please see. For example, here is 100 ampere and here is 80 ampere. The summarize can be represented by I1 equal 100 minus 80. This is the equivalent. Current will be 20. Okay, no problem. Please see. If you consider this by II is the representation of summation of generation and load. No problem? Please see. I1 here will be I from 1 to 2 and 1 I from 1 to 3. This is a KCL equation. Injected current in the bus equal this current plus this current. No problem? No problem, Arisada? Okay? Okay, let's see. I changed the color. Okay, let's see. Yes, Alisa, the Kirchhoff current equation, or we can represent by KCL. Kirchhoff current law. Okay, no problem. Okay, please see here. We can write I1 equal. You can write for one I12, please here, you can write V1 minus V2 divided on Z112. Okay, this is I12 V1 minus V2 divided on ZY2 plus for I3 I13 here 1, 2, 3 plus V1 minus V3, okay, divided on Z13. Correct? Right, I13, this is current in this line. Okay, right? I13. It is clear, right? Right, Hamid? Okay. Please see here. We can write for this simple network I1 equal. We write 1 divided Z12 or 1 divided Z13. We represent this by admittance. Admittance between 1, 2. No problem? And here is the admittance 1, 3. No problem? Correct? Yes? Okay, please see. We write I1. We write V1. We have Y2. Y12 plus here is 1 Y13. Okay, no problem. Plus for V2 you have only minus Y12. Okay, and for V3 have minus Y13. Correct? Correct, Ahmad? Bashar, right? Iman? No problem? Please see again, it is clear. Bashar, refresh your screen. Refresh your screen. Okay, you can write for I2. Again, you can write for I3. Okay, no problem? No problem? Okay. You have, for example, in this very simple network, you have I1, I2, I3. Okay. We can write in a matrix representation, matrix form representation. We can write I1, I2, I3 equal a matrix V1, V2, and V3. Okay, please see. For example, for first row of this matrix, please see here. Come back to previous example. Please see, this is the first term of the matrix. This is the second, and this is the third in the row. In first row will be Y1, 2 plus 1, 3. Here is minus 1, 1, 2, and plus the third is minus 1, 3. Okay, Ella, right, Carol, okay. We can write I1 equal Y12 plus Y13 multiple to V1 and minus Y12 to V2 and others, okay? And you can write also for this year and reach to this terms and others, okay? No problem. Please see, this is called injection current vector. We represent VI bus. I bus is the vertical vector including injected current to bus 1, injected current to bus 2, and injected current bus 3, and so on. Okay, the dimension of this vector is same of dimension of the network. For example, if you have a network with 100 bus, you have here a vector with 100 dimension. Okay. Here is called this matrix the Y bus matrix, or is called admittance matrix. And this is the vertical. This is the vertical vector for voltage of bus. Okay. The V bus including phasor of the voltage bus 1, bus 2, bus 3, bus 4, and bus N. And here is the injected power I1, I2, I3, I4, In, and this is the Y bus. Y bus has n to n dimension. Okay, the n is the number of buses in the network. Okay, this is called the network equation for power systems. Okay, Iman, no problem. Okay, it is correct, Mr. Zer, Miss Saad, and Miss Iman, Mr. Bashar. It is correct, no problem. Okay. Okay, I will send you in WhatsApp group some exercises for you, and I want to calculating and solving this problem and sending by WhatsApp or email address to me. Okay, my email address is right. Okay, please see if you want to send me answer to a question in subject. Please write power system 2 in subject, power system 2. For example, problem 1. Please see. Please write in subject of emails, power system 2, power system analysis 2. For example, problem 1, problem 2, problem 3. PS2 is constant, and the P1, P2, P3, for example, P1 for problem 1, P2 for problem 2, and P3 for problem 3, and others. Okay? No problem? I will send you the problems by WhatsApp today or tomorrow, and I want to come back to me by answering this problem and sending by email or WhatsApp. Okay, no problem? Okay. Okay, come back to the slides. Okay, in continue of our lecture, we refer to three-phase circuits. Please see. In balanced three-phase circuit means, for example, please see, we have three-phase generating unit, okay, and load, for example, is three-phase, okay. If the voltages, please see, if the voltages in this here is constant in magnitude, but the angles between the voltage source in phases have 120 degree, and here the load, the impedance, this here similar to this impedance here, similar to this impedance here. This is called balanced Y connection, three-phase circuits. Let's see. For example, here is V with angle 0. Here is V angle minus 120. And here is V with angle plus 120. This is a balanced three-phase generator. This is a balanced three-phase load. Connection is Y connected. This is also here Y connected. Okay? It is correct? No problem? I want write the reactive power, active power, cosinus phi and others for three-phase circuit. Okay? Until now, only we discussed about single phase, but continue with three-phase circuit. Okay? This is a three-phase balanced generation. This is three-phase balanced load. Okay. Let's see. If you consider, for example, EAN, come back to slides. Let's see, for example, here is N, natural or neutral point. Here is A. For example, this terminal is called B. This terminal is called C. And this point is called neutral or ground point. Okay, let's see. For example, EAN, voltage between terminal A to neutral equal 10 with 0 angle, and EBN 10 minus 120, and ECN 10 plus 120, or this. This means, please see, this means if you consider EAN with angle 0, this will be CN, and here is EBN. This phasor rotated in frequency of the network. For example, in Iran, frequency is 50. Okay, in 1 second, rotated 50 times. Okay, this is minus 120. This is plus 120. Okay, because we can write EAN in this here 10 with angle 0, EBN is 10 minus 120, or let's see, or we can write leading by these angles. This angle is plus 20, 40, 240. Okay, we can write EBN 10 minus 120 or 10 plus 240, and the ECN here ECN 10 plus 100 or minus 120 to 240. Okay. Let's see the line to neutral voltage magnitude in this example is 10 volt, and EAN is reference phasor because angle is 0. The phase sequence is called positive sequence ABC. If you consider an observer here, if rotated this phasor, this observer first CA, second CB, and finally CEC. This means a positive sequence. The sequence is A first, B second, and C third, ABC. Okay. Okay. For this balanced three-phase, we want to calculate line-to-line voltages and others. If you consider here, for example, come back to the slide. For example, if you want to calculate this voltage, AB is called line-to-line voltage. You only need write EAN minus EBN. Let's see. EAN minus EBN equal EAB. If you calculate, you can reach to this. And for EBC, reach to these and others. Okay. This means it is very important. This means if you have voltage between the line and the neutral, for example, here voltage is 10. If you calculate voltage between line to line, this voltage will be radical 3 multiple on 10. This means voltage, please see, this means voltage between line to line in three-phase circuit will be radical 3 times in comparison with single-phase voltage. Please see. For example, in three-phase line, one phase, two phase, three phase. If voltage between this phase to ground is 230 volt. This is voltage level for consumer in Iran, Iraq, and others. If you want to calculate voltage between the phase A and B, this will be radical 3 multiple on 230 will be 400 volt. Okay, correct? Okay, if you let me, I will continue from balanced three-phase current in the next week. in this year C E A B E B C E C A with be radical 3 multiple on voltage magnitude in single phase with angle plus 30 and others. Okay, we reach to this here, and we continue our lecture in next week from balanced line currents. Thank you for your consideration, and please waiting for sending exercises for you in WhatsApp group. Okay, if you have any comment, please let me to know. If you have not, I want to say you fi amanillah and khuda hafiz and goodbye and good evening. Good evening in Arabic, Sabah al-Asr. It is correct? Sabah al-Asr. Sabah. Yes. What is good evening in Arabic? Good evening. Masa al-khair. Okay. Masa al-khair. In Farsi, we write Asr al-khair. No. Shab Bekhair is the good night. Good evening is Asr Bekhair or Masa al Khair. Okay, Masa al Khair fi amanillah, and see you inshallah in next week. Thank you for your time and for your consideration.